Welcome to Krishna's classroom. Good morning, everybody. We continue from where we left last time. We were discussing the shortcomings of the Riemann integration. Now, the second part of this, namely the lecture I am giving today, concerns with some more shortcomings, and let us recall that one of the major drawbacks we found was that the class of Riemann integrable functions, if we introduce a metric using the Riemann integral, is not a complete metric space, which makes it difficult to do analysis. And we also gave some example to show that this is so. So let us look at some other aspects of the Riemann integration. In fact, see, the classical notion of integration, and before the concept of Riemann integration came into being, was that integration was considered as a reverse process of differentiation. That is, as soon as the calculus developed, the concept of differentiation came on, then the inverse process was called the integration, or what we had was that following. At that time, we were only looking at what are called the elementary functions, or the combinations of elementary functions, and we had extensively methods of differentiation and so on. So certainly the reverse process is certainly not a bed of roses, in the sense that often all inverse problems are difficult, and given the problem was this: given a function f, defined real valued function ab, assume f is an elementary function. The problem was that does there exist a function f of x such that f derivative of x equal to f of it is assumed that there exists such a function. Okay, because at that time we were working with only smooth functions, and that was the reason. Therefore, you see that f derivative of x equal to fx, or f was called the integral and was designated by so as soon as the concept of Riemann integration came into being, it was found that a very large class of functions can be integrated on the interval AB. In fact, all continuous functions defined on the interval AB belong to that. Bounded functions with some restrictions belong to that. In fact, all Riemann integrable functions we denoted by RAB, and the fact that CAB, the class of all continuous functions, is a subcollection of that, shows the Riemann integrable functions form a large class bigger than the class of continuous functions. Then of course he said that if the function is Riemann integrable on the interval AB, then it is also Riemann integrable on subintervals of the type AX or X belonging to F belonging to RAB implies F belongs to AX therefore this integral was sensible. Therefore for all functions integral a to x ft dt defined a function on capital F of x for every x belonging to A. This was possible. So naturally, one asks the following question. Is F equal to F derivative? That means that involves, is F differentiable? Everywhere. On AB and F derivative x equal to f. This was the question that you asked. Now, what happened was that this was no more. So in fact we could have second fundamental theorem of calculus true for such functions, but it does not follow that capital F is differentiable everywhere and f derivative is equal to small f. So, you see, the earlier notion, the classical notion was this, that integration was considered as the inverse process of differentiation. Therefore, once the function is given, if you could somehow find out the integral of that function, then it is differentiable and function. When this is true for all smooth functions, it's a result that is true for all smooth functions. But it's not really true even for continuous functions. It is not. Yes, because Riemann integrable functions are larger than the continuous functions, so this could not be true. But for continuous functions, possibly one could make a statement. And in fact, what happened was that this relationship had to be redefined. So the causality was the breakdown of charming results that f derivative f is differentiable and f derivative in fact, you see that one could even consider functions which have discontinuities at a countable points, still Riemann integrable, and Gx defined by zero to x, 0 to x not differential. not differentiable. Let us look at this example. This example is fascinating. Therefore, I just do this. Let us construct this example. Now, this is a very famous example due to Riemann. Let us consider, these constructions are very useful in analysis. Let f be defined from the interval minus half to half to R, a real valued function, be defined by fx equal to x for minus half less than x less than half and equal to 0 for x equal to minus half and x equal to. That means it's a function of this kind. And the function is has its graph like this. Now to put this bracket, it shows that the function has values 0 in these two endpoints. Now what one does is we extend this to the whole of R such that sort of periodicity, using periodicity you extend this. It's possible. And then that leaves you with a function of this kind. And so on. So you have function defined like this at, so this is the point minus half, minus 1, minus 3 by 2, and here it is half, 1, etc. So you have at these points, the minus 3 by 2, minus half, half, 3 by 2, etc. The function takes the value 0. So it's a function with discontinuity at infinitely many points on the interval on R. Now from here we define a new function. Now define a function R from R to R. This is the real line, this is the function R by Rx equal to sigma n equal to 1 to infinity f of divided by n square. Now you see that this infinite series is convergent for every x. Why? Because fnx is bounded by in fact half. Okay, therefore it's quite easy to see that the series that you get will be something like m into sigma n equal to 1 to infinity 1 by x square, majorized by that. Okay, therefore for every x this converges. And a function r is well defined. So r is well defined. And it has discontinuities at several points. Now because of you are taking fnx, f itself has discontinuities at several points like minus 5 by 2, minus 3 by 2 or 2n plus 1 by 2 for all values of n. Now you see that fnx makes the, as with n, with each term you see that the discontinuity spreads. So this is what makes the function discontinuous at several points. And in fact you have this property right, and r is a bounded function. Further, this needs some analysis, but I am not going to do that. For x equal to m by 2k, then rx plus means x approached from the positive side is, or the value of the function and approached from the positive side is rx minus a square, and rx minus, that is approached from the left side, is equal to rx minus plus where m and 2k are relatively prime. So r is discontinuous if and only if x equal to m by 2k with where m and k are integers, of course, runs over all integers. So you see that this function, if you look at this function and look at the on any interval AB, for epsilon positive, d epsilon, that means the oscillation is of the function at that point is greater than epsilon. This is equal to the set of all x for which omega is greater than epsilon is at most a finite set. Therefore, d epsilon is a null set which implies R is Riemann integrable over the interval. Okay. So we have constructed a Riemann integrable function with infinitely many points where the function is discontinuous. At the same time, on any interval AB, and this is what you have. So it's actually at a countable number of points, this function is discontinuous. Nevertheless, this function is Riemann integrable. And therefore, for this function, gx equal to integral a to x rt dt is well defined. In spite of the fact that R has discontinuities at a countable number of points, and it's a Riemann integral. And one could no longer claim that g derivative exists at all points. One could no longer say that g derivative equal to R for the over the interval A. Now, you see, we ask the following question. So what happens is that it is even possible to construct a function. So one could even construct a function f such that f derivative exists everywhere, but f derivative is not bounded, and hence f derivative does not belong to 0. Therefore, in this case, obviously, one could no longer say because this doesn't exist, is not Riemann integral. We'll give an example, cite a specific example now, which will give you some insight into that. In fact, these kind of functions are very useful in constructing such pathological examples. Define fx equal to x squared sine 1 upon x square for x not equal to 0 equal to 0 at x equal to 0. And of course, you take x belonging to interval 0. Now, you see that this function very rapidly oscillates. So, it's something like this. The graph looks something like this. See, this function. The function oscillates between plus x square and minus x square, and you also see that the function, so it's bounded by plus x square and minus x square obviously, and as x tends to 0, you see that 1 by x square becomes 0 very frequently, more frequently, or it's equal to, runs through the points 1 by n pi. If you take x square equal to what you call 1 by n pi, then you see that you get sine n pi and appearing more frequently towards 0 to 1. So what happens is, in the vicinity of 0, the function oscillates rapidly, which in turns mean that the tangent to the function will be changing sign far frequently. Okay, and let us look at whether this function is differentiable. Now, first of all, you see that this function only point where it is, there is some doubt about this is this. That is, you have to find out what is fx minus f0 divided by x. This is equal to 0. So at 0, the derivative exists. What about at other points? At all other points, the derivative exists because this is a nice function. Okay, it's a nice, smooth, differentiable function. So at all points, the function is differentiable. So f what about f derivative of x? Two x minus -2 x to the power 2 by x cos this is the derivative that you have at x not equal to 0. And you see that this becomes unbounded in the neighborhood of f derivative exists everywhere unbounded. Okay. Therefore, now you see here you have f dash not bounded, okay, and you can even construct a function f with bounded derivatives where f derivative is not Riemann integral. Okay, maybe it is worthwhile look at the construction of such a function. So what one should see, it is nice to see how this construction works. That's why I am devoting some time. I have done it in my previous lecture on this topic in some detail when we considered the Riemann integration theory. But let me just recall it once again because it is somewhat, I can qualitatively explain how such a function is constructed. So what we take up next is construction of a function which is differentiable everywhere and having a bounded derivative, still it is not Riemann. Okay? Because these kind of constructions give lot of insight into the intricacies that exist in the relationship between continuity and culture. So we will take it up now. Okay. It's a bit of a involved construction which involves, recalling something about C alpha. I will do that. But before that, we will build up the ingredients required to define such a function. And I will just quickly run over this and then we can get the required function defined. So our objective is construction of a example, construction of a function on 0, 1 which is differentiable everywhere at every point and with bounded derivative but not the derivative being not Riemann integral. So what we want to do is we want to construct a function on the interval 0, 1 which is differentiable at every point, that is the derivative exists everywhere and it is bounded but the derivative is not Riemann integral. Therefore, once again the causality is this relation cannot be Gx equal to integral 0 to 1 is no more valid. Okay, and this also serves as a nice example for many situations. Okay, let us go about constructing it. So how to construct this? First define for A belonging to R a function fa R to R as follows, that is fa of equal to x minus a whole square 1 upon x minus a and 0 So this is at x not equal to a, this is at x equal to a. So the function is once again of this type. This is a. So you have this is x minus a whole square and minus x minus a whole square. These are the two curves there. And what you have is it oscillates. This is f. This is the function f. Now you see the oscillation becomes rapid here, and you see that the zeros of this function starts appearing frequently and gets as it gets closer and closer. Now you see that it's quite easy to see that this function is differentiable everywhere, and you can even compute the derivative. I mean, like the one that we did, but one difference is that, see, here in the earlier function we were looking at sine 1 by x minus a whole square, okay, and we are not making this to oscillate that rapidly, but still it oscillates rapidly, okay. So it is sine 1 by x minus a, okay, right. Now you see that fa is differentiable. At fa 0 is 0 and differentiable everywhere. You can easily show that fa 0 is 0, fa a is fa derivative at a is 0 and fa a vanishes. See, f a derivative vanishes at an infinite set of points. It's quite easy to work it out. So if you look at the derivative of this, you can just define even. I have drawn it only for x greater than e. Yeah. So on the other side there is a similar pattern coming. That doesn't matter. That is not relevant for us. And you can work it out actually. What is going to be the derivative? Equal to minus cos so you can easily see that this is a bounded function, okay, right? Because this part towards a is towards x equal to a will be nearly 0. So this is certainly bounded, and this is also bounded. Therefore, this is as a bounded derivative. So you see that this has a bounded derivative. I'm just qualitative. I think you can actually estimate it. Now what we do is, in fact, the art of defining construction of such a function is this. From this we construct a new function. So this is the step 1. The step 2 we construct a function defined as follows. For a comma b belonging to R with a less than b, let we write alpha a to be supremum of x for which a is less than x less than a plus b by 2, which is the midpoint of the interval, and f dash a equal to 0. Now what happens here? See, you have the interval ab and you are taking a function like this, bounded between x minus a whole square and minus x minus a whole square, something like this. Now you see that there is the function as f derivative is this function, and you see that this f derivative oscillates rapidly. Okay, or in short, we are looking at the situation where this is fa, then we are looking at situation where finding out points where this would become this set of points we are looking at, where the function's derivative vanishes. And this is the point a plus b by 2, midpoint. And you see, you are taking up that the supremum of, you know that this is bounded by a plus b by 2. Set of all zeros of f derivative of a is bounded by the you are looking at the zeros of this, and the zeros of f derivative is bounded by a plus b. Therefore, you have got a supremum x's, and that supremum is designated by alpha a. Now we will define the function f of a b. That means it is going to be defined on the interval a b. X you define by the following: f a of x on a less than x less than alpha a. And f a is a constant function alpha a on the interval alpha a less than or equal to x less than or equal to b minus x minus b minus alpha a minus a. And the function is defined as f a b plus a minus x for b minus x, see, alpha a minus a less than or equal to x less than so that is the definition of this on the interval AB. So x belongs to the open interval AB. Okay. So how this function is crafted? It's better to, I am not going, you can work it out. This is the actual definition of the function. But what it turns out to be is the following. I think I can give you a idea of how this function looks like. So on the interval AB, you see it is symmetric about the midpoint. So you have the interval AB. Then this is the midpoint A plus B by 2. And what you have is this. The function is this is the function. And you see this point is where it bends down, and this point is what you call alpha. This is the point alpha, where the tangent becomes parallel just before A plus B. And you see, now what we do is, on this portion, you take the value of the function at alpha A and then connect with a constant function, and then symmetrically you just take the reflection of this function. So this up oscillates like this, and its constant function here takes the reflection on this, and you see that you are taking the reflection of this, and you have it's the reflection of this. I'm just taking, so you have, it is symmetric about the function is symmetric about A plus B by 2. That's what you can infer. So what we are doing is, we have the function here and just reflect it on this line x equal to A plus B by 2, or you take the reflection on define it over to extend it. This is the function that you do. So I'll just mark it with a color. So this is what you have. So this is how you mark it. Now you immediately observe that this function is differentiable everywhere. The one point where you have some doubt is at alpha A. At alpha A, you can easily see that it is so, because f derivative on this side is going to be 0. That's how we have picked up the point alpha A. It's a constant function on the other part. Therefore, you see that the derivative becomes a continuous derivative. Similarly, we are taking the reflection, and you see that this function has whatever behavior is there at A, there is a similar behavior at B. Okay. Now you observe that f derivative of AB is bounded, F is bounded, FAB is differentiable, AB, and you also have F derivative of AB bounded. So it is a bounded derivative everywhere on the interval AB. So you see that, in fact, you can show that F derivative of AB oscillates between +1 and -1 near B. Okay, right. So the next step is crucial. So we have got the ingredient now. In step 3, we consider the Cantor set C alpha for C 0 less than alpha less than 1. Take some alpha that lies between 0 and. Now, how did we construct the Cantor set? See, to recall, what we did was looked at the interval 0, 1, took the middle portion and cut out an open set symmetric about this. We call this I11 or something like that. And then you took the complement of that. As a complement was a closed set. It's a closed set. And the next stage, what we did was, we picked up the middle of this interval, and then from there we removed a open interval of length. This is alpha by 3. This is of length alpha by 3. This is of length alpha by 3 square. And again here also we removed something which is of, so this is again alpha by 3 square, and step by step we removed middle alpha by 3 to the power n and so on. Okay, so that's how we constructed this. And we had the following, you recall the notation that I did in my last lecture. Make use of that, and I am not explaining more than what I said just now, because it's all available in my previous lecture, how this is constructed. It's quite important, and you see that C alpha turns out to be 0, 1 slash, remove from it, union 1 to infinity, union j equal to 1 to 2 to the power n minus 1, ij n minus 1. So this, I believe the notation is right. Anyway, you see, this is what we called AN. Okay, so it is 0, 1 slash AN, n equal to 1 to infinity AN. So this was in our earlier notation. Each AN was a finite union of intervals. Okay. Now go to the details of that, which is not very relevant here. Okay. Now what is relevant is that ij n minus 1 is an open interval removed from 0, 1 at the nth stage. Now what we do is we take this as so you see, so this is of the form, so inj is of the form sum a and b such that this is what you have. Now we define a new function, capital F, this is equal to 0 for x belonging to CL. And this as f a b, which we have already defined, x if x belongs to I minus 1 set as AB for n comma j such that 1 less than or equal to for every n j with 1 less than or equal to j less than or equal to the power n. So what you do is, you see how this C alpha is constructed is that take the interval 0, 1, start removing open intervals, and eventually you get the leftover will be what is called C alpha. Now for at the nth stage, if you take one of the intervals, not only for all n, you take one of those intervals of the form AB, and then for that you define FAB. So what happens here? The sort of function that emerges is this. This is the interval 0, 1, and you see that this is the midpoint, and this is the first interval that you have removed, and there you see that there is a function something like this. You have this type of function, and it's connected like this, and then it's symmetric you see. So it's very interesting when you look at this. I will draw the function here. Draw the function here. From here we can construct it. Now you see that you take the interval 0, 1. You have the midpoint. You have removed an interval of length alpha symmetrically placed here. Now here what you do is this. You have this function. So this is the function AB. You have, you see, you have similarly you will be removing a smaller interval here, a smaller interval here, and once again you will be removing such open intervals. On each of these open intervals, you will be fitting a function like this. So it will cover all the portions other than the points in the Cantor set. And at Cantor set, at the points in Cantor set, we set the function to be equal to 0. Now you see that all these n points are going to be in the Cantor set, and there the function is equal to 0. Okay. Now let us see what happens to this function. Now you see that the function capital F is then a, so x C alpha, F is differentiable. And f derivative of x equal to f derivative AB x with appropriate AB that you use. F is differentiable at f is differentiable at points in C alpha. So you can see that where this matches with a point in C alpha, now you see you are going to have the derivative will be constructed, will be computed as follows. You take FAB divided by x and divide by x minus a, and then proceed to the limit as x tends to a, and that clearly exists. Let's look at the definition of the function. And you can show that f derivative is not continuous. At C alpha. That is easy to see. Although f derivative is bounded by 3. For x belonging to 0. So it is a bounded derivative but not continuous at the points in the Cantor set C alpha. Okay. But we know that, so at each point in C alpha, continuous. Although it is bounded. Although it exists everywhere on 0, 1 and is bounded. Therefore, once again, zero one, because the lambda of C alpha is equal to alpha is positive. So it is not discontinuous at a set of points of on a null set. Okay, therefore this is not an integrable function, and therefore once again so you see the whole classical result on what you call the relation between the integral and a given function as an antiderivative collapses here. Okay, so a lot of change takes place in the notion of integration. Now that is the first thing that we observe. A second problem, of course, another problem is this, that if f is Riemann integrable, first we have the fundamental theorem of calculus. For functions in R. So let f be a map from AB to R and f belong to Rx. That means it is Riemann integrable on the interval. Assume capital FA equal to is defined as 0 and f of x is defined as, which makes sense, 0 to x, what you call ft dt for x belonging to AB. Then what we have is this, what we can prove is this. First one, f is uniformly continuous. On AB. Second property is that if f is continuous at AB, then f is differentiable at x and f derivative of x equal to f of x. The third property is this: if G is a differentiable function, such that G derivative of x equal to f of x, for every x belonging to AB, then for every x comma y belonging to AB, you have gy minus, that is the second fundamental theorem of calculus. And this, you see, is nothing but your G derivative. Okay. So there is lot of qualifying conditions. Okay, you see that if small f is continuous, then the fundamental theorem of calculus, as we knew in the classical stage, that is differentiation is the, or integration is the, is anti-derivative, is clearly true, but otherwise such a statement cannot be. Okay, so this is one of the major things that happened with the advent of what are called the concept of Riemann integration. Now, I think I'll stop here and have a look at the convergence problem in my next lecture, most probably too, because it will be too stretched. I don't want that to happen. Thank you very much.